All right, this is going to be a review over section 1 through section 5. We're going to look at plain old solving, like in number 1, 2, where we're solving by just taking a plain old square root. And then we'll go on and we'll look at some more complex problems where we're multiplying or dividing with roots. And then later on, we'll get into conjugates with number 7. Number 8 is just going to be like rationalizing harder problems, and then some other simplifying things. We'll also be going over fractional exponents like in number 11 and number 12, and hopefully this will help out and make things a little bit easier. So if you need to, jump through the video. Otherwise, I'm just going to start number 1. So we're plain old solving. To get rid of our square, I'm going to take a square root. So I'm going to square root x squared is equal to the square root of 4. Whenever you put in a root, anytime you place the root, you have to do a plus or minus. Anytime you put in the root, you have to have the plus or minus. So my square root of x squared just turns into plain old x equals plus or minus 2. All right? We put in the root, we have to put in the plus or minus. Now let's look at number 2. X equals square root of 4. Now that one, the root is already written. So we do not need a plus or minus. This is just going to be x equals 2, right? No plus or minus, right? I know that number 2 is pretty easy, but I wanted to make sure that we see the difference between when do we need a root and when do we not need a root. Or excuse me, when do we need a plus or minus and when do we not need a plus or minus. All right, so hopefully that helps, and let's move on. For the next set of directions, we're supposed to simplify and rationalize when we have to. So we have the cubed root of 50x squared z to the 5th times the cubed root of 15y cubed z. They both have a cubed root, right? They both have the same index. That means we could write them under one big root. So I'm going to write a big cubed root. This is going to be 50x squared z to the 5th times 15y cubed z. Now, because this is a cubed root, I'm looking to get things in groups of 3, right? Cubed root groups of 3. My 50 and my 15, there's a few different ways we could deal with the constants, but what I'm going to do is I'm going to break them down into their primes and list all the primes. So 50 breaks up into 25 and 2, 5 and 5, and also I have 15 breaking up into 3 and 5. So I'm just going to circle all my roots. I have 5, 5, 2, 3, and another 5. So starting off my next line, I have the cubed root. And now I'm just going to list all my primes. So I have 3 5s. So I have 5 cubed. And then I have times 2 and times 3, right? So that's 5, 5, 5, 2, and 3. Yep, that's all of them. All right. Now for my, what do I want to do next? I'll do x's next. So I've taken care of this, and I've taken care of that. For my x's, I have 2 x's, so I'm just going to leave it as x squared. That takes care of this guy. My y's, I have a y cubed. Now for my z's, I want to list them in groups of 3, right? I have 5, 6 z's, so that's like 2 groups of 3. So z cubed, z cubed. Now this step, I'm going to actually simplify. Actually, let me rewrite that a little bit. All right. Now I'm going to look for all my pairs of 3s, or my groups of 3s rather. I have a 5 that's going to come out front. I have a y that's going to come out front. And I have 2 z's. So it's going to be z squared out front. Left underneath the root, I have a 2, a 3, and an x squared. That's going to turn into a 6x squared. So I can erase this and make it just a little bit prettier. This is my answer. This is my final answer. Right. You can always write out all these steps. Normally I don't. Normally I skip some steps, but you're always welcome to do that. All right, moving on to number 4. Here, we're going to have to rationalize, right? There's nothing that we can cancel, but we could make the denominator a little bit prettier. To start off, I'm going to break my root up over the top and the bottom. So I have the square root of x over the square root of 8y. Now, before I try to rationalize, I'm going to try to simplify all my roots. That's going to be my bottom root this time. Well, 8 breaks up into 4 and 2, 2 and 2. So I have a pair of 2's and a single 2. So this will turn into root x over, I have a pair of 2's that come outside, so 2 root 2y. Now, we've done all the simplifying we can. We're going to have to rationalize. So to rationalize, we're going to multiply by a square, something with a square root. And I want to make a pair of things so that I can get the 2 and the y out from it. I have one 2, so I need another 2. I have one y, so I need another y. Right? If it was a cubed root, you'd have to get 2 more, right, of each of them. So my next statement is going to be, my numerator, I'm just going to have big square root, and I can just multiply those together. It's going to be 2xy. In the denominator, I have this 2 out front, and then I have root 2y, and root 2y just gives me a plain old 2y. So multiplying that denominator together, I get square root of 2xy over 4y. And that is going to be my answer. All right. Number 5. Again, we're going to just have to rationalize our denominator. For starters, we look for things that can cancel in our fraction. We want to make sure that our fraction is as reduced as it can. The 3 and the 4 can't cancel, and the a on top can't cancel with anything on bottom, so that's all that we can do. We're going to break it up over the root. So it'll be the cubed root of 3a on top and the cubed root of 4b squared c on bottom. Now, before we move on, this number here, this 4, I'm going to break it down to its primes, and I'm going to list it as its primes. Well, 4 breaks up into 2 and 2, so this is going to be the cubed root of 3a over the cubed root of 2 squared b squared c. Right? By breaking the 4 apart like this, it's going to make the numbers stay smaller. Otherwise, we'd have to multiply by a couple more 4's. So now I need to multiply by a fraction to rationalize the denominator. It's going to be a cubed root because that's what we're dealing with this time. I want to get sets of 3, right? In the last problem, I wanted to get sets of 2. So I have 2 2's already. I need one more to make it a set of 3. So I need 1, 2. And then I have 2 b's already, so I need one more. And I have 1 c, so I'm going to need 2 more. All right. Now, our numerator just goes all under that big root together. So I'm going to have 3 and 2 can give me 6. Then I have a, b, c squared. And then on the bottom, this one's kind of simple. We have the 2 squared and the 2, the b squared and the b, the c and the c squared. They all can come outside of the cubed root, and they turn into just a 2bc squared. Nope, not just plain old c. All right. If you want to, we can write that extra step there. And I'm just going to write the denominator step to the side here. So we have the cubed root of 2 squared b squared c times the cubed root of 2bc squared. Together, right? Whenever we multiply that together, it gives us the cubed root of 2 cubed b cubed c cubed, which gives us 2bc, all right? That's just an aside. Almost every single time you're going to do that in your head, but I just wanted you to be able to see that. All right, moving on. Let's look at number 6. Number 6, with that 1 in the numerator, there's nothing special that I'm going to be able to do, like canceling wise. So I'm going to just break it up over the fraction. I'll have the square root of 1 over the square root of 5x cubed. Now I want to simplify as much as I can. The square root of 1 on top is just a plain old 1. Now on bottom, I have an x cubed, right? That means I have one pair of x and then an x left over. So my pair can come outside, and then my 5 stays underneath, and then my leftover x stays underneath. Now I'm going to need to rationalize the denominator. So I'm going to multiply by something with a square root, because that's what we're dealing with. I need pairs of whatever's underneath my root. So in this case, to make pair of 5s, I need another 5 and then another x. My numerator now becomes the square root of 5x. My denominator, I have my x that sits out front, right? And then I have my 5 and my 5 that turns into a 5. And then I have my x and my x, which turns into an x. Multiplying together the denominator, I'm going to get the square root of 5x on top, and then 5x squared on bottom. There we are. Number 7. Now here, all we're going to have to do is rationalize the denominator. There's nothing we can cancel there. What's going to be special about this one is that we have a subtraction sign there. Whenever you don't have just... Hey, have a great weekend. Whenever we just have the subtraction there, we have to use a conjugate instead of, like normal, we would just multiply. So we have 5 root 3 minus 1. Oh, excuse me, the conjugate's going to have a plus 1 there. 5 root 3 plus 1. Right? The conjugate, you write whatever you have there, and you swap the sign, right? So if this was a plus, we would be writing a negative. Now, sometimes it is useful to write these all in parentheses, just to help us whenever we're distributing. On the numerator, I'm going to distribute that 2, so that's going to be a 10 root 3 plus 2. And in the denominator, I'm going to have to multiply out the 5 root 3 and the 5 root 3 will give me a 25 times 3. Then I'll have a plus 5 root 3 minus 5 root 3 and minus 1. Notice that these inner ones will cancel each other out. So we'll have 10 root 3 plus 2 in the numerator. And then in the denominator, we will have, what's that going to be? 75 minus 1. Yep. And then we will have, to combine the denominator there, 10 root 3 plus 2 over 74. That's that. Number 8. Here we're going to have to rationalize the denominator again. There's no canceling that we can do. Most of the time, if you have an addition sign there, you're not going to be able to cancel a lot, right? If you have an addition or subtraction, it makes it a little bit more difficult to cancel. You still can sometimes by factoring, but normally you can't do that quite as much with these problems. So the denominator, though, what can we multiply by to get rid of that cubed root of x? Well, it's a cubed root, so we're going to need to multiply by a cubed root. Cubed roots mean that we want a pair of 3. So we're going to need 3 x's. We have 1 x so far, we're going to need 2 more. So my numerator, whenever I distribute this guy to the 2 into the cubed root of x, I'm going to have 2 cubed root of x squared plus cubed root, well, I've got an x and then 2 more, so it's going to be x cubed. The denominator, I will have, what is that going to be? Well, I have 1x here and 2x's there, and then it's a trio, so they can come out and it'll just be a plain old x. Now we need to check that everything is as simple as it can be, and if we look right here, this guy there can actually reduce. So we're going to have 2 cubed root of x squared plus x over x. All right, and let me circle that because that is our answer. Number 9. This one again, we're just trying to simplify. We've got 2 things that have addition between them and no fraction or anything like that. What we're going to end up doing here is we're going to try to reduce our roots first. We're going to reduce them as much as we can. So 32 will break up into 16 and 2. 16 will break up into 4 and 4, 2, 2, 2, 2. Now I know there are other ways to do this that might be a little bit faster, but the factor tree I find to be the most tried and true way that it works best for me. If you find another way to do it, that's okay with me. 50 will break up into 25 and 2. 25 will break up into 5 and 5. So we have a pair of 5s and a single 2. So going back to our first radical, we have a 3 sitting out front, and then we have 2 pair of 2's. So it's going to be 2 times 2. And then underneath my root, I have a 2, right? That leftover 2. For the second radical, I have a 2 sitting out front to begin with. And then I have a pair of 5's that are going to come outside. And then underneath my root, I have that leftover 2. So 12 root 2 plus 10 root 2. Now, whenever you get to this step, think about it as if it were 12x plus 10x, right? 12x plus 10x. You add those together and you would have a 22x. Well, that's what we're going to do here too. We're going to say, well, this is 22 root 2, right? Because they have the same root right there, right? I think they're called common radicals. You're able to add them together. A lot of the time, whenever I see that, it helps me to remember what do I do with a plain old variable. And that same rule applies here. All right, number 10. Again, we have an ugly root, so we're going to use a conjugate. So I'm going to have to multiply by something. I'm going to say root 7 and root 2. This time it's going to have a minus sign between them, right? Because it given to us is a positive, so I'm going to have to multiply by one with a negative. Again, sometimes it is useful to put parentheses around things. I guess it wouldn't be useful there, but useful over here. And then we can think about our distributing. So that numerator, we have 2 root 14 times 7. This is going to be 2 root 14, and I'm just going to put times 7 under there. And then minus 2 root 14 times 2. In the denominator, I'm going to have root 7 times root 7 is going to be 7. Root 7 times negative 2 will be negative root 14. Root 2 times root 7 is positive root 14. And root 2 times negative root 2 is negative 2. Notice that the middle pieces cancel. That's going to be a pattern with all conjugates. Now this will combine to be I'm going to leave the numerator the same. 2 root 14 times 7 minus 2 root 14 times 2 all over 5. Now, we can probably see here that our numerators are going to simplify some. I hope that you're seeing that. Oops, I lost my roots. All right, there we are. So let's take our 14, and it breaks up into 7 and 2, right? So I'm going to change both of my 14s into 7 times 2. So 2 root, and instead of 14, I'm going to say 7 times 2 times 7 minus 2 root, oops, that root shouldn't have been as long, I'm sorry. There we go. 2 root 7 times 2 times 2. That's all over 5. Now here we have a pair of 7s, and here we have a pair of 2s. So this is going to turn into, our first radical right there will be 2 times 7 root 2. Our second radical will be 2 times 2 root 7, and our denominator will be 5. To wrap it up, we multiply what's in front of our radical. So I'll have 14 root 2 minus 4 root 7 over 5. And we are finally done with that problem. All right. Number 11. We're just supposed to solve. So we're just supposed to list our x equals and get it as simple as possible. So first off, we're going to get our x by itself. So this will turn into x to the 1/4 equals 3. To get rid of the 1/4, we're going to take it to the 4th. Right? So then we'll have x equals 3 to the 4th. That's the same thing as 3 to the 4th is 90, or 81. 81. So x is 81. All right. Number 12. Again, this is very similar to the last one, except this time we're going to get a -3 over here. So just like last time, we're going to take it to the 4th. And then we'll have x equals, and -3 to the 4th is also positive, 81. All right. Let's look at actually, you know what? I think I meant to do something different with these problems. Let's look at another problem here. Let's call this x, or I'll write it in a different color. X to the 3/4. Nope. How about 4/3? Yeah, 4/3. Yeah, let's look at this problem here. We'll call this like 11b. We add our 3 over, just like before. So x to the 4/3 is 3. Now, to get rid of that 4/3, I'm going to have to put it to the 3 over 4, the reciprocal of our x exponent. So this will be x equals 3 to the 3/4. Now I'm going to put this in radical form just so that we can kind of see what I'm going to mean here in a second. This is the same thing as x equals the 4th root of 3 cubed. And I'm going to write it like that. Now that 4th root wasn't there originally, right? Right up here, we took the 4th root. We wrote that in there, so we need a plus or minus. all right? Even though it didn't look like we were taking a fourth root, we need that plus or minus, right? And we only need the plus or minuses if it's an even root, right? If it's 2, 4, 6, 8, right? If it was the cubed root, we would not need it. So this is going to be, our final answer is going to be plus or minus fourth root of 3 cubed. All right, make sure that you have that plus or minus there. Let's do the same thing with the next problem. We're going to call this one 12b. And this one's going to be x to the, what did I say up here? We'll say 4/3 plus 3 equals 0. So this is the same thing as x to the 4/3 is -3. Just like last time, I'm going to take this to the 3/4. All right. This will be x equals -3 to the 3/4, which, as we said before, that means that x equals plus or minus the fourth root of -3 cubed, right? Last time it was positive. Well, that doesn't work. We have a negative under the root, so we're going to say no solution. All right. So something that I don't think I emphasized well enough before is that whenever we take a exponent, or whenever we take something to the power of a fractional exponent, you need to make sure that if you're using like an even denominator or an even root, you put those plus or minuses in, or you make sense like in 12, or if you make sure that it makes sense like in 12b. In 12b, taking the fourth root doesn't make sense. Taking something to the power of 3/4 doesn't make sense, right? In number 11b, taking something to the 3/4, it works, it makes sense, but we can't forget that plus or minus, all right? Moving on, number 13. Well, to solve this one, we're going to just take both sides and we're going to cube it, right, to undo that cubed root. So this will be x minus 2 equals 4 cubed. And I don't remember what 4 cubed is. What is that? It's 16 times 4, right? Is that 50 something? 64. So this will be x minus 2 is 64. So x equals 66. On all of these problems where you have a root like this and you're finding some exponents, you want to plug back in to check your answer, right? We want to make sure that there's not any of those bad answers. What are those called? I can't remember. It starts with an E. Let me look. Extrapolate. What's that called? Extraneous solution. We want to make sure that we don't have an extraneous solution. So I'm going to plug back in. So I'll have the cubed root of 66 minus 2 equals 4. And I really want to know, does that equal 4? Well, this is this cubed root of 64 is 4. And I typed that in my calculator just a second ago, so I know that the cubed root of 64 is 4. All right, number 14. We're going to start this one off by squaring both sides. So I'll square the left, square the right. This will give me x minus 6 is 36. So x equals, what is that going to be, 42. Now, just like in the last one, we need to plug back in and check to make sure that works. So I'm going to have the square root of 42 minus 6 equals -6. And I want to know, does that equal? So this is the square root of 36 is -6. And hopefully you're seeing that, well, that doesn't work. You can't get a negative out of a root. Now let me erase the stuff that I had right at the very beginning, and maybe we'll be able to see that. This is one of those problems that you could have just looked at and said, well, there's no solution to that. You can't get a negative out of the root, right? Number 15. This one we're going to be squaring also, just like in the last one, only this time we have a binomial on the right side. So this will give me x plus 10 on the left, and on the right it will give me 100 minus 20x plus x squared. This has turned it into a quadratic equation, and I'm going to order it from highest power to lowest, and I'm going to get everything equal to 0. So 0 equals x squared minus 21x plus, is that 90? 90. Now, I'm going to need things that multiply to be 90 and add up to be negative 21. I'm going to take 90 divided by 3 and see what that is. 90 divided by 3 give me 30. 90 and 2 give me 45. That doesn't make sense. 5 and 18 go into 90. Can I add those together to get 21? What if I take 90 divided by 15? 15 and 6, that's it. 15 times 6 is 90, so I'm going to use a negative 15 and a negative 6. So this is going to be x minus 15, x minus 6. From here I can say x minus 15 is 0, x minus 6 is 0, so x is 15 and x is 6. Now, we need to check our answers. We need to plug back into our original and make sure that they make sense, that they actually work. So I have root, I'll check the 15 first. 15 plus 10 equals 10 minus 15. So this will be root, what's that, 25 is negative 5. Well, that doesn't work. You can't get a negative out of the root, so it's not going to be 15. Trying out our next one, we're going to have root 6 plus 10 is 10 minus 6. This is 16 is 4, or square root of 16 is 4, and yeah, that works. So the x equals 6 does work, right? So that is our only answer here. Alrighty, number 16. Here we're going to add 2 to the other side, so we'll have 2x to the 4/3 is 162. Before I can do my special power stuff, the power, or the exponent, only goes to the x. That 2 does not belong to it. So I'm going to divide everything by 2. Now I'm going to take my funky exponent. So this will be to the 3/4. So this will be x, let me change colors back to my blue, x equals, and let's write it as a root. We have the 3/4, that means it's the 4th root, so that means if I have to have a plus or minus, because it's an even root, of 81 cubed. So x is plus or minus, well the 4th root of 81 is 3 cubed, so x is plus or minus 27. Now let's plug back in and see if that works. So I have 2, and then, well, let's look here for just a second. This takes it to the 4th power, so it doesn't matter which one I plug it in. It's going to force it to be positive. That makes it kind of easier because I'm only going to have to plug it in one time then. I'll use positive 27 to the 4/3 minus 2 is 160. So this is going to be 2 times, well, 27 to the 4/3, that's like the 3rd root. The 3rd root of 27 is 3 to the 4th minus 2 is 160. So 2 times 81 minus 2 is 160. 160. So let me type in 2 times 81 minus 2. Yep, 160 is 160. So both of those answers are good. Number 17, we're almost done. We're going to have x to the 1/2 is 5. To undo the 1/2, right? Remember that this, let's just write it in radical form. This is the square root of x is 5. To get our real answer, we're going to square everything, so x is 25. This is one of those that we can kind of just plug in and check in our head. We plug in a 25 right there in our x. X to the 1/2, or 25 to the 1/2 is 5, minus 5 is 0, so that one's good. Number 18. Here we're going to have to square it because we have a square root there. Before we square it, we want to get everything alone. We want to get the square root alone, rather. So I'm going to get my square root alone, so root x equals x minus 6. So whenever I square everything, I'll get x equals x squared minus 12x plus 36. So x squared minus 13x plus 36. So what can I use here? What is 36 divided by 2? 18. That doesn't work. What about 36 divided by 4? 4 and 9. So 36 splits up into 4 and 9. You add those up and you get 13. So I can subtract them together and get negative 13. So 0 is x minus 4, x minus 9. So I'm going to skip that step that I wrote in the last one like this and just say, well, x is 4 or 9. Now I need to plug in and double check, does this work? So I'm plugging back into my very original. So I'm going to say, well, the square root of 4 plus 6 equals 4. So 2 plus 6 equals 4. Well, that's not true. So it's not 4. And then for my 9, I'll say, well, the square root of 9 plus 6 is 9. 3 plus 6 is 9. Well, that one works. So 9 is our answer. All right, number 19. Now, I don't think these root ones like this are that difficult. After you kind of do a few of them, they get pretty easy. Starting off, we're going to add this whole guy over to the other side. Whenever we add it over, it becomes positive. So I'll have root 6x plus 5 is root 5x plus 6. Now I square both sides of it, canceling out their roots. 6x plus 5 is 5x plus 6. Subtracting, I get x is 1. This is one that we should check. Actually, we're supposed to check all of them. So let me plug back in. We have the square root of 6 times 1 is just 6 plus 5 minus the square root of 5 times 1 plus 6. Well, 6 plus 5 is the same thing as 5 plus 6, so that's going to check out. So our answer is 1. Number 20. Here again, we're going to have to square both sides. You'll notice that 2 sitting out front. We can't get rid of the 2 before we square them, so we're going to have to square it with the 2. Now think about it this way. This 2 that's in our exponent goes to this, and then it goes to the root. So we're going to have a 4 and then x minus 1. And the 26 plus x, right? So this will be 4x minus 4 is 26 plus x. So that will give me a 3x is 30 and x is 10. I need to make sure that that actually works in my my equation here. So I'll say, well, 2 root, what's that? 10 minus 1 equals root 26 plus 10. So this would be 2 root 9 equals root, is that 36? Yes. So this will be 2 times 3 is 6. So it works out. That is our answer. All right. I hope this helps you out. Let me know if you have any other questions.